Alright, so this is really the second podcast that goes along with this objective because it's simply simple ionic compounds. So we also call these binary ionic compounds because they're only consisting of two different elements. So you have a metal and a nonmetal. However, so just in your notes, some ionic compounds contain a metal with more than one charge. So I call these either-or metals. And these occur in the middle of the periodic table. So anything to the left of the alkaline earth metals and anything to the right of the nonmetals. So all those metals in the middle are called transition metals. That's a special name for them. However, there's three exceptions, and those are bing, bing, bing. So if it's a metal other than silver, zinc, or aluminum that's in the middle, it is an either-or metal, or it's a metal that has more than one charge. Okay? So just like our last podcast, we're going to talk about naming the compound, and then we're going to talk about writing the formula. So naming the compound is simply this. The metal is written with a Roman numeral, which we have to figure out. Okay, so it's a little bit more difficult than our first naming. First naming, alkaline metals are always 1, alkaline earth are always 2, and bing, 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 always 1, 2, 3. So those are always metals. And now we're going to go to either or metals. So the metal is written with a Roman numeral, which we have to figure out, followed by the nonmetal whose suffix is changed to "-ide". So nothing changes with the nonmetal portion, only the metal part. Okay? So if we were to find Cu on the periodic table, okay, we would find that it's in the middle. Okay? So I'm going to immediately write copper. And I'm going to also write, I'm going to leave a space. You might even put parentheses over here. And I'm going to put iodide. All right? And there's really, copper has two different charges. You don't need to memorize this because you'll always know it, or you'll always be able to figure it out. But copper is either a 1 or a 2. Okay? So in this instance, what we kind of have to figure out is iodine has what charge? So if we look on the periodic table, we're going to find that iodine has a -1 charge, or iodide does. So if copper and iodine are in a 1-to-1 ratio, because if I look at my formula, I have 1 Cu for every 1 iodine, right? So there's really a 1 after copper and a 1 after I. So because it's in a 1-to-1 ratio, if I have a -1 iodine, I'm going to have a +1 copper. So I'm going to put the Roman numeral 1 after copper. So this is really called copper 1 iodide. How come? Because copper, in this instance, is copper 1. Let's skip down to the fourth example real quickly and kind of see how this works. So this is also copper iodide, because we have Cu with iodine. But in this case, if I kind of come over here and put like a -1 above my iodine, I find I have 2 iodines. So iodine is contributing a total of -2 charge, which means that copper must be contributing a +2 charge. But how many coppers are there? There's not a number, which means there's only 1 copper. So this copper must be a +2, so that it neutralizes or equals the charge that the iodine is contributing. So the Roman numeral tells us the charge. So because I have a +2 charge, I'm going to use the Roman numeral 2 after copper. So this is really copper 2 iodide. Okay? Next one, magnesium. Well, that's weird, Mr. Burkett. If we look on the periodic table, it is the second column, so it's an alkaline earth metal, so we don't have to use a Roman numeral. Okay, so I'm kind of I don't know, not necessarily trying to trick you, but just showing you the difference between if we know the charge and if we don't know the charge. So magnesium will never have a Roman numeral. How come? It would be redundant to put one there. Magnesium is always a 2. It can never be anything but a 2. So we don't like to be redundant in chemistry. If we were to say magnesium 2 oxide, people would just go, duh, it's always 2. Okay, so there's no need to put a 2. Our last one, I'm just going to write over here so it's a little bit bigger, but we have Fe2O3. So I have iron. I won't do parentheses this time, but we're just going to maybe put like a little underline, knowing that I need to leave a space there. Oxide. All right, so we have no idea what iron's charge is. It's in the middle. It's a transition metal. But we know what the nonmetal's charge is. So in this case, it's a -2. So if I have -2 times 3, I get a -6, correct? So what times 2 would be a +6, because my charge that my metal contributes must be equal to the charge that my nonmetal contributes. So if nonmetals are contributing a -6, metals must be contributing a +6. So what is this unknown up here above iron that we multiply by 2 and get a +6? It's a +3. Okay, so in this case, this is iron Roman numeral 3 oxide. Kind of the same thing applies if you watch the first podcast, kind of crisscross. If we cross Chris, or do the opposite thing, so this 2 on my iron is due to this being a positive 2. So this 3 on oxygen must be due to iron being a plus 3. And again, just be careful with this. If my bottom subscripts were simplified, you could get the wrong answer. Okay? So if we did this example, let's just do FeO. FeO. You go, oh, there's a 1 and a 1, so if I crisscross, this must be a plus 1. But it's not a plus 1, because what is oxygen's charge? It's a negative 2. And if these are in a 1-to-1 ratio, then this iron must really be a plus 2, which is iron 2 oxide. And I'm just realizing that this got cut off of your screen. So this is really iron 3 oxide. I don't think the oxide showed up. Okay. The next part, though, I don't know, writing its formula. Oh, let's look at the bullets, the asterisks real quick. The Roman numeral always tells us the charge on the metal, not its subscript. So if you see the Roman numeral, it will almost never equal the subscript. In certain instances it does, but by and large, I would say 90% of the time, make sure that your Roman numeral doesn't match the subscript on the metal. Okay, it might match the subscript on the non-metal, but not on the metal. Okay, so as we get down to the bottom, writing the formula, if you read this, the positive charges must equal the negative charges. Again, think least common multiple. So this one is really not that bad, writing the formula of a transition metal, because we're going to do the same exact thing we did with just looking at the periodic table. So we have nickel. Oh boy, what's its charge? If we look on the periodic table, we're going to go, I have no idea what the charge is. But remember, the Roman numeral tells us what the charge is. So this is a plus 2 charge. And oxide is a negative 2 charge. Oh look, positive and negative equal, so it's just NiO. Done. All right, iron 3 sulfide. So I'm going to write Fe. And it happens to be a plus 3. How come? The Roman numeral is 3. And then I'm going to write sulfur. It's a chalcogen, so it's a negative 2. So what's the least common multiple of 3 and 2? It's 6. So I really want a 2 on my iron and a 3 on my sulfide, or I can just do the crisscross method, and my 3 becomes a 2, or a 3 becomes a 3, and my negative 2 becomes a 2. Okay, so we're never going to have negatives in front of our part as part of our subscripts. And then chromium 2 phosphide. Chromium, what's the Roman numeral? 2. So you don't even have to look on the periodic table if the Roman numeral is there, which is kind of nice. And then we have phosphide, which is a negative 3. And crisscross again, this becomes a 2, and chromium is a 3. All right, so that is the second part of naming. And I think you're well on your way to figuring this out.